Hi students, welcome back, and today we are going to continue our lesson on 11.3 gravitational acceleration and free fall. What does it mean by gravitation, acceleration, and free fall? Um, let's look at this. Isaac Newton is sitting under an apple tree. So, the thing it fall down. The apple fall down due to gravity. So I think we know that gravity in science is also considered as the law of gravity, the law of thermodynamics, and so on. We need to differentiate between the law and the theory. Usually law is something that is proved really correct. So of course, from here we can say that there is earth gravity that make the object fall down, and that's acceleration. Assuming that the acceleration of the apple, does the acceleration of the apple looks like? So I would say that the apple at first it start from 0. The speed is 0. So it will fall down, then it's getting faster, faster and faster and faster until it becomes 0 again, the speed. What if I put the apple in the sky? Let's say I put the apple, I use a plane. Okay, how to draw a plane? With a mouse. Let's say this is a plane, and I throw the apple come down. So what will happen? So of course the apple is getting faster and faster and faster and faster. But will the apple get faster unlimited? Like here faster, here faster, here faster, here faster, here faster, here faster, and then boom, there will be explosion. But of course there is not. When you drop the apple, it will become faster, and until here, I would say it is the constant speed. It won't get even faster already, okay? It will because that is the fastest that it can go. We call it, it has reached the terminal velocity, we call it. Is there any word as terminal velocity? Wow, so many things. Anyway, just go up first. It won't go faster anymore because it has reached the terminal velocity or the constant speed. If not, I throw something, I will get faster and faster until you go to the speed of light, and then it suddenly disappear from the space because it is so fast that the space don't get it. But it's true, just in case you say that will something move faster, it can travel, I think, travel slower in time. If you move faster, you are traveling slower in time. So if you move very fast, either you stop the time or you can go back in time. This one I'm not sure, but one thing I'm very sure, if you move fast, it will slow down the time, and this has proven, especially the person that sit in the rocket. When they sit in the rocket, they go up to the space, and the space their turn is faster. So when they come down to earth, they always need to adjust their clock because the time in the clock is not same with the time on the earth. But it's only slowed down a few seconds, not a lot lah, maybe 6 or 7 seconds. So the person that the astronaut always have the time, me and him also the same, 99 years old, but the thing is he is younger than me 6 seconds if both of us die at 99 years old, for example. So if you move faster, the time actually go slower. So yeah, so this is the constant speed. You cannot go faster. So we call this also as a free fall. Free fall means when you fall down, there is nothing that block you. So you just free fall. The acceleration will, if I can draw a graph. So let's say this is the speed. This is the time. Right? This is the time. So I will say that the speed will be something like it will go from slow, then fast and fast and fast and fast, and then it will reach a terminal velocity. It will still very fast, but it cannot go forever go up. If not, later it will reach the speed of light. So it has reached the terminal velocity. Okay, and all the object is experience gravitational acceleration. In one sense, the thing will go faster because there is gravity that is pulling the object. So it will go faster. So we call it as a gravitational acceleration. And gravitational acceleration, the unit is 10 ms negative 2. So I just put here 10 ms negative 2. Or sometimes we use the gravitational force, we put it 10 Newton. So you're also equivalent to your weight, because as you are standing, it's pull you go down, so you got weight. Let's say I'm 50 kg. When I stand on it, if the gravity will pull me down, I will be 500 Newton, for example. So that is the gravitational acceleration, 10 ms negative 2, and it is constant. The acceleration is constant. Maybe I actually want to show you a video. So just let me share you a video about this experiment, about how the acceleration work in a free fall. Because if a student asks me, you put a bowling ball and a feather, when they both fall, are they fall at the same speed, or feather fall slow but the bowling ball falls fast? But eventually when you see both of them fall at the same thing, proving the theory that the gravitational force acceleration is 10 ms negative 2. Because if you say 10 ms negative 2, it must be the same. Bowling ball and the feather, they drop down, it must be the same, because you say that it's 10 ms negative. So let's watch this video to see whether is that the case.
And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of... Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force.
Yeah, so from the video we can see that if not later I put the link below so that you can see. You can see that at first, if I'm to drop the bowling ball and the feather, I just put the the bowling ball will go down faster. Okay, it will go down faster. But if I put it a vacuum, no air inside, I put a bowling and a feather, both drop at the same speed. It also proved that both has a free fall of 10 ms negative 2. Acting on the object, everything is the same. The reason the feather is slow to fall down, why the thing is slow? Because of got air. Inside got the air, we call it air resistant. Okay, so the air resistance actually block the thing. But if you are bigger, means you are slower to fall down. Because when you are big, when you fall, you need to push all the air away. So we call it air resistant. Then it will come down. But the bowling is small. It is not I mean, yeah, I know it's heavy, but it doesn't really matter how heavy. As we can see, even though you're heavy and light, it doesn't matter. It's just because of the density. The bowling ball density is high, so if when it fall down, the air not so blocked. Unless I take the bowling ball, I cut until like a powder, very, 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 very small powder, and I throw the bowling ball, the bowling ball sand, then it will slowly fall down, or maybe slower than the feather because it got higher air resistance. But what is the conclusion? The conclusion that we know is we can say that this is true. 10 ms negative 2 is the gravity act the same because we can see feather and the bowling ball fall down the same thing. 10 ms negative 2 is the same to all the object. We also conclude that the feather falls slow because of air resistance. Then we can also conclude. And we also can conclude number 3, both the speed is the same, the free fall, the acceleration is the same. So there's a force acting on it. So basically I want to show you that's called the free fall, but of course at a certain time it will reach terminal velocity. So this is what this is an experiment to determine the gravitational acceleration. So he just put this thing and let this thing fall down, and then this the ticker tape direction of the motion. Start from where? Start from left or start from right? I think it start from here because here is 0. Here is 0. Then here is faster. Of course, here it will drop down. It will again the same ticker tape. So initial velocity, if you want to make it easier, you just make it 0.02. One dot is 0.02. So here to here is 0.02. Here to here is 0.02. You need to use a ruler. So you measure lah. Let's say this is 1 cm. So you use 1 cm divided by 0.02, you get the speed. Let's say here is 2 cm. 2 cm divided by 0.02, you get the speed. And then acceleration, this is v, this is u. So v minus u over t, you get the a, acceleration. You get what I mean or not? Okay, let's try to do this. I know lah, we didn't do experiments, so we cannot do this. But anyway, let's try. Okay, let's say here is 1 cm. Here is 1 cm divided by, so the initial velocity I put u is 1 cm. 1 cm divided by 1 dot is 0.02. 0.02. I will get, I put here as 1 divided by 0.02. I get 50. 50 cm. Oh my goodness, I'm using my mouse to write. It's so difficult. Oh, so my hand is so tired. 50 cm as negative 1. Okay, so this is v equals to, let's say the v here is 2 cm. So here is 2 cm. So 2 cm divided by 0.02 second, you get how many? 100, is it? 100 cm negative 1. So formula for acceleration v minus u over t. So 100, I don't want to write the unit because I'm using my mouse. I just want to make it faster. The minus 50 divided by the time. The time is here to here. Here to here is, let's say it's 5 tick. 1, 2, 1, 2, 3, 4, 5. 5 tick. So 5 times 0.02. So you get 50. Let me press my calculator. 50 divided by 5 times 0.02, you get 500. 500, what's the unit? cm. I'm not writing m because I didn't use meter divided by second. I use cm, so I write cm. 500 cm as negative 2. So this is the answer, assuming this is the experiment. What is the common mistake that students do? Again, just want to mention sometimes what students do the mistake so that you won't do it. Sometimes students count like this: 1, 2, 3, 4, 5, 6. So they use 0.02 times 6. Then you get it wrong. Okay. Depending on how you want to do it, but you can see that this is a very good example. He only used the middle part. So your middle 1, 2, 3, 4, 5. Okay. For me, I like to use the front part. Okay. 1, 2, 3, 4, 5. Beginning to beginning. Like if you want to use behind, or you want to use the middle, which I think actually the middle is the most accurate one. Because middle means the exactly the time for the speed, if you understand what I'm talking about. That is the middle, because eventually if you really consider properly, this speed is different, 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 this speed is different. So every distance the speed also is different, maybe different by 0.001, but you don't know because we are just human, unless we are God or Superman. So we don't know, but we know that it's actually very very tiny. That's why the book say they use the center, because we just estimate the at least we estimate by using the midpoint of the 0.02 second. So at every place there's a different speed. It could be the difference of 0.00000000001. Who knows, right? Okay, then you get the answer. Remember to get the answer correct in terms of the unit. If they give you the cm as -2, please do cm as -2. If this one is meter, convert it to meter. So how to convert this to meter? 500 cm. Let's try to convert this into meter. I'm using my mouse to write. Okay, very difficult. Okay, 500. I copy back the same one. 500 cm. 500 cm divided by time s -2 divided by s2, also equivalent to 5 meter, because 5 cm equals to 5 meter. 5 meter divided by 1 s -2, 1 s2. So the answer equals to 5 m s -2. So here is 500 cm. Change it to meter, it will become 5. Okay. Okay. Any problem? No problem. Right? Free fall. So again, from the experiment, free fall, what does it mean by free fall? a sheet does not freely fall because it is affected by the air resistance. Yes, just now we see already. Either you put a paper, a feather, or what. The thing is uh, not really free fall because of air resistance unless you put in the vacuum. So in the video, unless you put in a very big vacuum, you put the two things fall, it will be free fall. Okay. So this one is also not really like free fall because you can see the wind. The wind will be moving like this. The wind will be moving like this. So it depends. The speed won't be so high. Okay. Okay, so yep, that's it for this video. So I will see you again next time. You can always try to do your exercise, and if there's nothing, I mean, you cannot understand, you can post in the comment below. So I see you by next week, okay?
Okay.
Okay, thank you and bye bye.
Thank you, teacher.